Oh, and maybe one more just general announcement-y thing, homework-y thing, before I crack in on today content-wise. I've just recently gotten a decent amount of homework turned in late. And like, I know I make arrangements with people at the end of class saying, yeah, I understand you've had a situation, like, I'll accept the homework late. But like, I forget everything by the time I make it up to my office if I don't get it in writing. So like, if I've taken points off because I've said you turned something in late and we had a conversation which I said I wouldn't take these points off, just like, let me know. Put a Canvas comment up, talk to me in my office, and I'll get those fixed. Neato. All right, so let's begin with just a reminder of a bit of terminology and a little fact from last time. So, and this is just like a reminder about this comment in the notes and what multiplicity is, because we will use it in a moment to do an example. So if p of x, a polynomial, factors as a polynomial q times some linear polynomial raised to a power. So there are two bullet points I'm going to put down here. Near x equals c, the graph of y equals p of x is close to So, right, that looks really technical. What does this say? This says that if you can pull out a bunch of linear factors, Gesundheit. And in fact, you've pulled out all the linear factors, so this remainder term, q of x has the property that it's not 0 when you plug in x equals c. Then the graph near x equals c will be given by just plug x equals c into all of the x's that don't result in a 0. And then just remember the x minus c to the p power. And this is now easy to graph. That's just a power function that's shifted a little bit to the right by c. And then if that q of c is like negative 23, it's flipped over and then stretched by a factor of 23. That seems sane enough? All right. The other comment is just a notational comment. This number p, I don't like that. I'm going to change the name of this polynomial to phi, just because right now p has two jobs. This number p is the multiplicity Right, so c is certainly a root of that polynomial, so it's a place where that polynomial is 0. This number p like says how much of a root there is. That notation feel okay? Yeah. So let's use this to do with it. Let's use this just to do some graphing manually by hand, and then we'll check. So I think, let's walk this one. So here is a polynomial, x times x plus 1 squared times x minus 2 cubed. I'd like to generate a graph by hand. I would like to have all of the zeros, all the roots, all the x-intercepts, those are all the same ones, indicated on the graph. I'm not worried too much about scale. So, let's start with this. Is it easy to say where the x-intercepts of that graph are? Where are they?
0, -1, and 2.
0, -1, and 2. Can you say why?
It's when all the x's equal 0, x is equal to 0 when x is 0, x is equal to 0 when
So I see a little factor of x, so that means x equals 0 is one of the roots. I see this, let's make the colors better. I see this x plus 1 factor, so set that equal to 0 to see that x equals -1 is a root. And set this last piece equal to 0 to see that x equals 2 is a root. Let's label them. There's one at -1, 0. 0, 0 is obvious. 2, 0 is there. Cool. All right. So let's just read the instructions. So I would like to have I want a graph that looks correct near those intercepts. So let's try to figure out how those graphs look near each of those intercepts. So to do that, we're going to use this sort of decomposition. So once you have something factored, grab all the factors that give you a 0 at that root, remember them, and then just plug in the x value that is that root to the rest of the factors. That make sense? Let's just see it in practice. Yeah.
Could you, we'll see it in practice, yeah, so, I just didn't quite catch it.
Yeah. So the game is if you want to graph near a root,
Right.
remember the factor that gives you the root.
Okay.
And then just plug in x equals that root to all the rest of the x's. And that's what we'll do right now. So near x equals 0, let's see, in that factoring, which of the factors gives you the root at x equals 0? The x, I guess. So I should remember this factor, the x factor, which is underlined in pink. So, I'm going to rewrite what's written above. Y equals x times, and now I'm just going to plug x equals 0 in for all the rest of the x's, because that's the location of the root. 0 plus 1 squared times 0 minus 2 cubed. That feel okay? All right. So that tells me a lot. That tells me that close to x equals 0, it's going to be a straight line. If I want to figure out the slope of that straight line, I guess I need to compute 0 plus 1 squared times 0 minus 2 cubed. And what is that in purple when you simplify that? I hear a -8. I hear a second for -8. Cool, yeah. So let's write that down. This is x multiplied by -8.
Would it be -7, where's the 1 go?
Oh, cool, let's do it in more detail. 0 plus 1 is,
1.
squared is,
1.
0 minus 2 is -2, cubed is -8, cubed, but they're multiplied, not added.
Oh, okay.
Yeah. So that tells me something. That tells me that near x equals 0, I should see a straight line of slope -8. And I'm not going to worry about having an exact scale or anything, but there should be a straight line of negative slope. Nice. People feel okay right now? Let's keep on trucking. Near x equals -1. Well, ask yourself, of the factors up there, which of those factors actually result in the root at x equals -1?
The x plus 1 squared.
The x plus 1 squared. So I should remember the x plus 1 squared. So y approximately x plus 1 squared. And then I'll plug in x equals 1, x equals -1, because that's the location of the root I'm looking at for all the rest of the x's. Because that's what this instruction says to do. Nice. So doing that, I see an x there, so that's a -1 times -1 minus 2 cubed. All right, so that is, x plus 1 squared. So that tells me that close to x equals -1, there will be a parabola. Times, what's the coefficient next to it? I just don't want to do it myself.
-27.
I hear a -27. Do I hear any disagreement? Because I think I disagree.
Oh, just 27.
I hear a positive 27.
I thought you meant like just the -1.
Ah. Yeah, right. The whole thing matters. So it'll be -1 for this -1 times -1 minus 2 is -3. Then you cube that. The cube of a negative is negative. 3 cubed is 27. And parentheses so I don't accidentally do subtraction. Feel pretty okay? Nice. So 27x plus 1 squared. So close to x equals -1, I should see a parabola. It'll be upward opening because that 27 is positive. It'll even be like super steep, but I'm not worried about having like correct scale information. I just want a very cartoonishly correct graph. So, be a bit of a parabola, close to there. And you know what, this is like step 3 that I'm doing right there. I'm gonna smoothly interpolate between these points. Can you do the same thing near x equals 2? So go through that same process near x equals 2, tell me what you wind up with.
I'm so scared to ask. Thank you.
Okay. Sorry, I'm terrifying. Anyone else? Okay. Cool. So, I guess close to x equals 2, what should I wind up with?
18 times x minus 2 squared.
And here at 18 times x minus 2 squared. Cubed? Did you say cubed? Well, whatever, it should be cubed. Oh, cool, that's another thing that's easy to graph. It'll be like x cubed, but then stretched by a factor of 18. And let's smoothly interpolate between, so it'll come in something like that. So that's already step 3 done. And now let's remember what happens when x is really big. So the philosophy is that when you plug in a really big value for x, you basically only see the leading term in the polynomial. And maybe we'll even do this way. So this y is equal to x times x plus 1 squared times x minus 2 cubed. So I'm going to imagine plugging in a gigantic number like a billion. If you plug in a billion for x, does that plus 1 actually make a difference? Not like a significant one. It does technically make a difference. A billion is not equal to a billion and 1. Does that minus 2 make a sizable difference? No. So when I plug in something really big, I can ignore all of those lower order terms. So this is close to being x times x squared times x cubed, also known as x to the 6th. So that tells me what happens when x is extremely big. The graph should look like y equals x to the 6th. What does the graph of x to the 6th look like?
Like x squared.
Yeah, like x squared, but like steeper. But I'm not going to be able to see that difference at this like cartoon style graph I'm drawing. Neato. How'd that feel? And we have now a graph that you can read some things off of. Like just by looking at this graph, does this function have a minimum value? And if I were to ask you like the x value that produces that minimum, like what does it sit between? Like, can you tell me anything about that? Like one-ish, though like, I don't know if I would trust that so much because I wasn't careful about that. It's definitely somewhere between 0 and 2. You also see that, oh, I know for a fact there's a local maximum right here, somewhere between -1 and 0. Because the graph shows there has to be. And let's just check that information. We have a computer, let's also just generate a graph using a machine. How'd we do? Does this look vaguely like the thing we have? Yeah. So there are some things that like are suspect. It looks like this local minimum should probably be a little bit lower than it's drawn because like that valley is in fact significantly lower than that peak is high. But I wasn't expecting any of that to be accurate because I wasn't careful about any of that. But you do know some things about the shape of the graph by doing this like very hand-wavy stuff. Cool. So, what do you think? You think you could do a similar problem on your own now? So, talk with each other, ask me questions if you like. Here's one last one. Sketch for me by hand the graph of x squared times x minus 2 to the 4th times x plus 1. You know what? How'd the exercise go?
Still going.
Still going. Okay, I should be patient.
When will you have your term grades posted?
Pretty quick after I finish grading. If I don't have it done by Friday, I'll be annoyed with myself. So like, let's say the weekend at the latest. If you're impatient and want to see like how you did, I do have part 1 graded. If you want to come by my office, we can talk about it.
Yeah.
Okay.
The bigger the next one, it's gonna be like. The higher the next one.
So, as you go through it, remember you can like talk to each other. This isn't a test, I'm not going to collect it. Once you have a graph, you can go ahead and check with the graphing calculator if you have one handy. If you have any questions, like you feel stuck on how to address one of the prompts, now's a great time to just like ask me what on earth I mean by this.
Oh, right, yeah. Thank you. Yeah, I don't really care. Yeah, it's just when the powers are the same thing, it's when the powers are the same, same variable, they give us one. It's like 2 to the 8 times 2 to the 8.
Alright, people feeling okay? Shall we come together? Alright.
I'm sorry.
So let's start with this. Where are the x-intercepts of this graph? Where are the roots of the polynomial? Yeah.
0, 2,
0, and I'm going to do some color coding. So
all right, all in that.
2, and you said -1?
Yeah.
Alright. And I've added this color coding so I can like say which piece resulted in the root. So which one of those factors gave you that 0 at x equals 0?
Square.
X squared. So I'm going to underline that in blue just in order to like make hopefully some of the next steps connect better. Which one gave you the 0 at 2?
X minus 2 to the 4.
Cool. And the -1?
X plus 1.
Awesome. Cool. And maybe I'll even color code the points on the graph. Oh, so you'll notice that like I've intentionally, well, maybe you didn't notice that I did it intentionally, but I've left off absolutely any hash marks from this graph. And that's because if I want to put any vertical hash marks, because I'm not being careful, they would definitely be wrong anyway. So I intentionally left the hash marks off because if I had, I'd be trying to convey more information than I'll actually be able to, and that information would turn out to be a lie. Like there might be some local maximum, but I have no idea the height of that local maximum because I'm not going to try to check it. All right, so let's play this local graphing game. Near x equals 0, what does the graph look like? A parabola. So I guess that means you got an x squared. And what's that x squared multiplied by?
16.
16. And, in fact, maybe I'll even point out this. Since I'm being so loosey-goosey with my graphing, like, I don't really record anything more than that 16 was positive. So, all right, cool. So, parabola upward opening. Near x equals -1.
It's a positive linear.
No, x minus 1. You said linear, but if I'm going for it, like the thing. That agree with what other people saw? All right, so close to x equals, oh, that should be a +1. Close to x equals -1, I should see a straight line of positive slope. So it'll crash straight through the x-axis positively. Close to x equals -2.
Another problem for Apple.
Another positive parabola. You know, that feel pretty okay? Groovy. So I'll put another one of those here. And I guess I better interpolate smoothly between. For really big x values, what sort of polynomial, what sort of power function is this?
7.
Degree 7?
Yeah.
Nice. And that's an odd power, so at the quality I'm going to be able to draw anyway, it'll look vaguely like x cubed.
Does it really matter? Does it only matter if it's only even or odd? You can determine the outcome no matter. Like this one's gonna be odd.
Yeah.
And it's also positive, so we know it's gonna start low and high.
Yeah, so, and you certainly even know that from like those
Yeah.
crossings. This one, like, you can't go back up, it has to go down. But doing this is still like a nice sanity check. Right, it's nice to have some amount of redundant information when you do stuff like this. If the redundant information disagrees with itself, then you know that something's wrong. Cool. People wind up with a graph something like that? How many people went and checked by using a machine to do some graphing? It agreed? Yeah, I mean like vaguely. I guess like I see 2 peaks there, and it looks like I have the second peak being taller than the first peak. Does that agree with what the computer said? I give it a 50-50 whether it would or not, right?
It's more like, and then it goes, drops, steady down, so that's kind of like.
You're saying they should be like taller?
Well, at least the left, because it feels like it's a lot steeper. Yeah. The middle one still, it was fine, it was just the left.
Ah, okay. Yeah, so the takeaway, that maybe is a point that I shouldn't belabor, is there's going to be information which you'll read from this graph, which, if it's not information that you checked, isn't information you can really trust. I don't actually know which of those 2 peaks is taller. Though I guess you do, since you looked at the computer graph. I do know, however, that because it went up and it came back down, there has to be a local maximum somewhere in the middle. There has to be a local maximum somewhere in the middle. Because it asymptotically looks like x to the 7th, I know that it doesn't have a global maximum or a global minimum. So the stuff that you can tell by doing this process. That feel pretty good? Nice. So, here's the power. If you can find all the roots of a polynomial, and you can factor it, then you can make lots of questions easy. You can make understanding what the graph looks like reasonably easy. So let's try to make some progress on how on the earth would you do that. So like, a generic polynomial isn't going to be handed to you as a factored thing. It's going to be a bunch of coefficients next to powers of x. So let's figure out how you would walk with that. So, but for a degree 2 polynomial, like it's somehow easy, right? Like there's a strategy that factors degree 2 polynomials when they have rational factors. Even when they don't, the quadratic formula tells you the intercepts, and you know they'll both be linear, so theoretically you just factor the thing. But what about like cubic polynomials, or degree 4 polynomials, quartic, degree 5 polynomials and up? Like, is there something like the quadratic formula? And let's just talk through some history. So the actual quadratic formula dates back to antiquity. It's hard to say like who the first civilization is to have developed a quadratic formula. Certainly there's record of like use of something that is equivalent to the quadratic formula in like the construction of the great pyramids. They wouldn't have written down things in the same way because like this way of writing down expressions with x's and like plus symbols between them is relatively modern. But there was that idea in like ancient history. In the 1540s, a mathematician named Cardano produced a cubic formula. So what does that mean? It's something like the quadratic formula that says if you have a polynomial that looks like ax cubed plus bx squared plus cx plus d equals 0, and you want to solve that, there's a formula for the solutions in terms of those coefficients a, b, c, and d. It's like kind of a long thing. It takes probably more than like a line to write it by hand. And there's some like variables that you should like set aside beforehand to write it down. If you go and look at like the Wikipedia page, you'll find a formula that you can unpack. It'll take maybe 10 minutes of reading to unpack the formula, but then once you have it, you have it. If you like, if you're the type who wants to learn how to program their calculator, you could extract from that the formula, and now your calculator can solve degree 3 polynomials. I'm not saying that that's something you have to do, but if you're the type who would want to do that anyway, go for it. So you can solve any degree 3 polynomial by a formula. It's a formula that no one ever talks about because it's too hard to use by hand anyway. That's a weird thing to say because Cardano definitely used it by hand. He was in the 1540s, he didn't have a machine. A few decades after Cardano, another mathematician named Ferrari produced a quadratic formula, which is a formula that solves any degree 4 polynomial. It takes probably about a page of text to like write down the formula. It's, big and ugly. But again, like if you have a computer, the computer doesn't care how big and ugly the formula is once it's written. So you can solve degree 4 polynomials on the nose. You can get exact formulas for them. And that was kind of the state of that for a while until the 1820s, when a mathematician named Galois, then aged 19, proved that there is no general algebraic formula for polynomials of degree 5 or more. So there is no quintic formula. And in fact, like Galois' book shows that that degree 5 polynomial, it has some roots. It has at least one anyway. You cannot write down its roots using any combination of addition, subtraction, multiplication, division, exponentiation, and roots. Its roots don't have that form. So, in some sense, trying to algebraically solve high degree polynomials is not possible, generally. But we're going to try to do it anyway. For like context, that's Galois at age 19. Galois died at age 21 in a duel. He was like kind of a political, let's say, thorn in the side of those in power. And there is rumor that the person who he lost this duel to was a professional marksman who was hired by the government to get Galois to challenge him to a duel, which he then won because Galois didn't stand a chance because he doesn't know how to use a gun. So anyway, I guess one lesson you can take away from this class is if someone challenges you to a duel, you should probably assume they're trying to trick you and say no. That, and even if you do win, like duels are illegal now?
Everything is legal in Germany.
I think also there. So, there's no algebraic way to solve high degree polynomials. There's no purely algebraic way. But you saw some strategies. Like, let's suppose I asked you to like ballpark what are the roots of this polynomial and I gave you access to any tools you wanted. What's something you could do?
Algebraically solve it, so add 1 to the side and see what x of minus x equals 1, or when those two variables equal 1.
Sure. Like that's a strategy, but like it's doomed to failure. You can't do it purely algebraically. That's like, and we're not going to prove that to you, like, if you would like, that would happen in like the second semester course on abstract algebra, which I believe is called Math 426. So the tools are hard to prove that, but like, it doesn't have an algebraic solution. Like, what's something you could do anyway, using a machine? Yeah, it's graphic. Like, you can always do that. The machine is just gonna plug in like a billion inputs. None of them will actually be the root of this polynomial, probably. But it's gonna get close. Minus x minus 1. Oh, cool. This looks like it has an x-intercept. Looks like it has one real solution. And Desmos is even willing to estimate it for us as about 1.167. So you can always do that. If you have a computer, you can do something like graph it. And you can ballpark the solutions. So it's just always something worth remembering that you have as an option. What I'm going to do for the next 10 minutes, and then all of probably like 2 more lectures, is talk about some tools that let you get definite information about polynomials, none of which will apply in absolutely every case. They'll give you some tools, that'll give you some options, those options won't always work out. But when they do, they can tell you really exact information. And here's the first tool. If you happen to already know a root of a polynomial, you can translate that root into a factor. So let's just say what I mean here. So here's a fact that I'll tell you. 2x cubed minus x squared minus 7x plus 6 equals 0, has x equals 1 as a solution. Should we check that? I think we should, because it's like easy to check anyway, because plugging in 1 is easy. I don't even need to write anything. 2 times 1 cubed is just 2, minus 1 puts us at 1, minus 7 puts us at negative 6, plus 6 is 0. Yeah, plugging in x equals 1 gives us 0. That's, I didn't lie to you already. Polynomial division then says that x minus 1 is a factor of this polynomial. So I can definitely write down this degree 3 polynomial as x minus 1 times something. And before we do anything, like, let's see what we could say about that something. What would the degree of that pink polynomial have to be? Yeah, degree 2. Because like, that one has an x in it. If you had like an x to the 5th in the pink bit, then there would be an x to the 6th after you multiply. But the biggest power in this thing is degree 3. So this is going to be a degree 2 polynomial. Ooh, so if I could factor it, I'd see a linear thing times a degree 2 thing. Linear thing tells me the solution x equals 1, but I already knew that one. Degree 2 thing I could use the quadratic formula on. So if I can find that degree 2 polynomial, I can solve with this polynomial equation. So let's just try to find that. And the whole philosophy there is polynomial division. How do people feel about polynomial division? People would say they feel like they know how to do polynomial division. People would be comfortable saying that they at some point have seen polynomial division and could probably remember it given some work. Okay, cool. I'm going to announce right now that there is already another recording posted for today, which is just me going through a long lecture on just polynomial long division. I'm going to try to do something in the 7 minutes that I have, but there's something that's an hour long just posted to the webpage that you can go through at your leisure. It's also in these notes, but if you want to see me talk through it. So here's the first just totally ad hoc strategy. Let's just try to factor this thing by grouping. And here's the game I'm going to play. I see a 2x cubed right there. If I saw in this polynomial 2x cubed minus 2x squared, I could factor an x minus 1 out of that. that would give me x minus 1 times 2x squared, I guess? So I'd like to see 2x cubed minus 2x squared in this polynomial. Do I see 2x cubed minus 2x squared in it? But could I? I could just stick an extra plus 2x squared in there as long as I stick an extra minus 2x squared in there. Let me show you what I mean, and then we'll have the algorithm started, we'll be off to the races, and we'll just iterate it. So here's what I'll do. I want to see a minus 2x squared. 2x cubed minus 2x squared plus 2x squared. This color. Minus x squared minus 7x plus 6. That's the same as the polynomial that's written above. But I've just subtracted and added the same thing. Cool. So, let's use that. So, this is 2x cubed minus 2x squared. That piece I want to hold on to because I know that x minus 1 is a factor of that piece. Now I'm just going to copy the rest of it down and look at the biggest degree term and iterate this. Plus 2x squared minus 2x squared is plus x squared minus 7x plus 6. So I haven't like really done much. I've like added and subtracted a term and then I've like simplified a little bit. Let's look at this plus x squared term. This one will be in full. So I see an x squared. What would I like to see next to that x squared for this factoring to walk? How about a minus x? So the whole game is I want things that this x minus 1 will factor into. So if I want to see an x squared, I'd like to turn this into x minus 1 times something. And I know the thing I'm going to have to multiply by. It's going to have to be x. That's the only way I'm getting an x squared out. So that means I'd really like to see x squared minus x sitting there. Do I see x squared minus x? Yeah, kind of. I see, in fact, a minus 7x. Let's just pull an x out of that. That feel okay? So, next line, I'm going to continue to have this 2x cubed minus 2x squared plus x squared minus x. And I pulled that minus x out of that minus 7x, leaving me with minus 6x plus 6. So let's just look at what we have. I want to factor an x minus 1 out of everything in sight. Could you factor an x minus 1 out of that? Yeah, cool. It's like 6 times x minus 1. Minus 6 times x minus 1. This purple piece, it's designed to have an x minus 1 sitting in it. That purple piece is x minus 1 times what? X, I think. The pink piece is also designed to have an x minus 1 in it, and what is that x minus 1 multiplied by? Ooh, so this is looking good, right? Everything there now has an x minus 1 next to it. So you can factor out an x minus 1. 2x cubed plus x minus 6 multiplied by x minus 1.
That'd be 2x squared.
I
Yep.
just do polynomial division, and I got that too.
Awesome, that's good. So,
Well, kind of. I got negative 2x minus x plus 6, but it's just the same thing.
okay, cool. So your
All the
remaining
last
factor
signs
would have
were
been
flipped.
minus x plus 1 is what you would have factored out. So you did like a thing on the synthetic division column?
Polynomial.
Interesting. You should have gotten the same thing.
Oh, well,
So timing is awkward. So if you like, what I just did was hopefully a step where that felt algorithmic. No steps seemed too mysterious. I just brute force pulled out factors where I could. I forced things to have the factors I wanted. That's like the slowest way to do this procedure. The slightly faster way is polynomial long division, which is logically equivalent and will really interact with this possible nicely. The most efficient way is synthetic division. And so we'll cover those two remaining strategies, I guess, next time. The timing's awkward, it would have been nicer to see all of these at the same time. Cool. And once I'm up in my office, I'll start updating the homeworks so that deadlines are all on Fridays. And if it looks like I failed to do that at some point, like shoot me an email because that's the type of thing that I'll fail to do at some point.
So I got, material letters.
thank you so much.